we'll do a little bit more with chapter 5, which again was talking about polynomials. If you remember, last time we started with just a bunch of definitions, so let's just kind of lightly review some of that vocabulary. All right, so for this, just some warm-up here to review some of the vocab from last time. We're going to determine if the given expression is a polynomial. And if we decide it is a polynomial, we're going to list the degree for the polynomial, the leading term, the leading coefficient, the constant term, and then the number of terms for that polynomial. So 3x to the fifth minus 4x to the negative 2 plus 8x minus 1. Is this a polynomial? Ooh, excuse me. Okay, so what do we need to check to see if it's a polynomial? Let's start there. We need to check that each of the things being added together is a monomial, right? Okay? Is 3x to the fifth a monomial? Yes. Is 4x to the negative 2 a monomial? No. So can this be a polynomial? No. So we're done. And again, the issue is we have a negative exponent there. How about this? Negative 10x minus 15x squared plus 6 minus 18x to the fifth. Is this a polynomial? Yes. Everybody agree with that? Okay. So since it's a polynomial, we also have to list the degree. What's the degree for this polynomial? It's what? It's not 7. It's not 8. It is 5. So the degree of the polynomial is just the degree for the biggest monomial. So if I look at the terms there, I have a degree 1, a degree 2, a degree 0, and a degree 5. 5 is the biggest degree for the monomial. That's the degree for the polynomial. Everybody kind of remember that now? Okay. What's the leading term here? Hi, Michael. We had a mix-up with the test, so that's postponed till next class. What's the leading term? So that's just going to be the term that has the highest degree. So it's negative 18x to the fifth. What's the leading coefficient? It's not 6. It's negative 18. It's the coefficient from the leading term. What's the constant term? It's not 18. It's 6. Why is it 6? It's the one without a variable. So the constant term has no variable attached to it. So that's 6. And what is the number of terms we have here? 4. Because we have 4 things that are being added or subtracted here together. We okay with that? Okay. Let's do one more. See if we can do this one mostly on your guys' own, as we kind of reviewed what a lot of that vocab was now, once through. Should be able to do this again. Is this a polynomial? Yes. Okay. So since it's a polynomial, we're going to list some things. So what's the leading term? That's the first thing we said we're going to list. Negative x to the 7th. Okay. That's good. And what's the leading coefficient? Negative 1. Everybody good with that? Okay. What's the constant term? 0. Very good. Why is it 0? Yeah, you can think of like having just like a plus 0 at the end of that, right? Oh, we forgot to do the degree. What's the degree here? That's 7, okay? And then the number of terms, it's really 4. So the plus 0 at the end doesn't count. Nope. That was just demonstrating what the constant term is there, but it doesn't count as an actual one of the terms, because you could just keep writing zeros at either end, and like, oh, I can have 0x to the 25th. You know, like, no, it doesn't count. Those don't count. Everybody okay with that idea? We feel all right on this vocab? Okay. So the next thing I want to do is talk about operations on polynomials? So the first operation we'll talk about is addition. So suppose I have a polynomial f of x that's equal to and another polynomial g of x that's equal to that. What if I wanted to figure out the polynomial f plus g of x? How do you think that we're going to add these two polynomials together? Yeah, we're just going to do f of x plus g of x, which means that we'll just combine the like terms. Everybody okay with that idea? Let's try to write our answer, though, in standard form. What do we mean by standard form? Good, so we want the leading coefficient, or the leading term in front. The highest degree monomial should be the first one, and then it should be descending, right? So what should be the first monomial we write here? X to the fourth, right? So we got that one. Then what? 4x to the third, okay? Notice we did that because neither of those had anything to combine, right? Okay, now what? So notice that the negative x squared and the positive x squared are going to add to give us 0. So we don't need to write that. Minus x, and then plus 8. So that's pretty easy, right? Everybody agree with that? Feel good about adding? Okay. What if we wanted to subtract? What if we are going to subtract these same two polynomials? Well, the same general idea that f minus g of x is just f of x minus g of x. Here's the catch, though, is that when I do that subtraction, I have to make sure I subtract all of g of x. It's very tempting for students to just subtract the leading term and not continue doing the subtraction. So the way I like to think about it is putting a negative sign out front and then making sure I distribute that negative through and basically turning it into this problem. Oops. Everybody okay with what we did there? So the number one place that mistakes get made when we do subtraction is forgetting to distribute that negative. Okay. So if I want to write this in standard form, what am I gonna write first? Negative x to the fourth, good. And then what? 4x cubed, good. And then minus 2x squared plus x plus 6. I agree. Everybody feel okay doing that? So addition and subtraction of polynomials, not too bad, right? What if I wanted to multiply them? If I wanted to do f times g of x. Well, surprise, surprise, it's going to be the same thing as f of x times g of x. So that's going to be that. How would you suppose I'm going to do this multiplication? Well, there's a couple of ways to think about it. So you could do like a modified version of FOIL, where basically I make sure I multiply each term from the first polynomial with each term in the second polynomial. So I could do like this, times this, times this, times this, and then this, times this, times this, times this, and then this, times this, times this, times this. That's a lot of things to kind of keep track of, right? We can see that. So, because keeping track of all those little multiplication problems tends, like when the polynomials get big like this, can get a little bit hard. What I'm going to do instead is a visual method. So what I'm going to do is I'm going to draw a grid where one polynomial is like the width and one polynomial is the height. Everybody's okay with that idea? So I'm going to draw my grid, and I'll have this first polynomial. And I'm going to include a 0x here. You're going to see why in a minute. And then I'm going to use the other polynomial as my height. And I'm going to include a 0x cubed here. You'll see why in a moment. Everybody okay with the setup here? And now what I'm going to do is I'm just going to do each of these little tiny multiplication problems. So for this square, I'm going to multiply its length times width. What do I get when I multiply x to the fourth by 4x to the third? 4x to the 7th. Good. And then I'll move, say, here. When I do this multiplication, I'm going to use that times that. So x to the fourth times negative x squared. What do I get when I multiply those together? Negative x to the 6th. Does everybody kind of get the pattern here that we're doing? Okay, let's take a moment, try to fill in the rest of this table on your own. I'll give you guys like a couple minute head start, and then I'll start filling in the table behind you. So go ahead and start filling in the rest of this little table on your own. Do these little multiplications. They should be things that you're capable of doing kind of in your head, right? Nothing is too big. You have just single number multiplications or additions, so, or single digit, I should say. So that should be pretty doable. I'll give you guys a little head start, and then I'll start filling in behind you. You guys see now why I included the zeros? Notice how the like terms are lining up here. So all of my degree 7 terms are on this diagonal. All of my degree 6 terms. All of my degree 5 terms. All of my degree 4 terms. Everything lines up on a diagonal, so it's really easy for me to combine the like terms. I don't have to sit there and hunt for like, oh, did I find all the degree 3 things to add together? No, it's not so bad. So the result here is 4x to the 7 minus x to the 6th plus 4x to the 5th plus 2x to the 4th for 5x to the 3rd, 6x squared minus 7x plus 7. Is everybody okay with how I kind of took my results from my grid and transformed that into my final answer? Should be pretty easy to do that, right? And this is the advantage of the grid, is the organizational part. It's easy to take your result and get your final answer out of it because everything lines up nicely. You don't have to like hunt to make sure, oh, did I do all the multiplications? Well, of course you did because you filled in every brick in the grid. Did I find all the like terms? Well, yeah, because they all lined up on one diagonal. You don't have to go hunting for them all over the place. So it's nice in that regard to make sure you did all the multiplying and that you collected everything back together. Is everybody okay with that idea? So the main strength here of this multiplication method is just the organizational aspect of it, right? It's kind of hard to mess that up if you can get the initial setup done correctly. Is everybody okay with that idea? Let's take a moment and go back and look at these 3 types of problems, adding, subtracting, and multiplying, and see if we notice a relationship between the degrees of the polynomials we started with and the degree of our answer. Okay with that? All right, so let's go back and look at the addition problem. So what's the degree for f of x? 3. What's the degree for g of x? 4. What is the degree here for f of x, or f plus g of x? That's 4. What do you notice? Did you notice those were the same? Right? What's going on here? The degree of f plus g of x is going to be, I guess I should say less than or equal to the maximum of the degree of f and the degree of g. Why did I put less than or equal to rather than a straight equal sign there? How could it end up being less and not equal? If it canceled out, great. So suppose f was equal to x squared plus 1 and g was negative x squared plus x. If I added those, the result would be x plus 1, right? Which has degree less than the maximum of f plus g. So we have to be a little bit careful. That's why we have a less than or equal to. Everybody see that? Okay. Let's look at the subtraction here. What's the degree of my answer here? 4. Okay. So what can we say again? The degree of the subtraction problem should be less than or equal to the maximum of the degree of f with the degree of g. For the same reason, right? That we have the same reason for the less than or equal. Let's look at the multiplication now. So what's the degree here for our answer? It's degree 7. How does 7 relate to the degrees of f and g? What happened? How is 7 related to the degree of f and the degree of g? So the degree of f was 3, the degree of g was 4. It's added together. So the degree of f times g is just going to be the degree of f plus the degree of g. Is it possible for those to be not equal? Can they cancel out? No, they can't, right? Yes, sir. Of course. So this is as good as we can do. That is what we'd call tight, because it is exactly that. It's not an inequality. And this is where we're going to stop here today.